On a quiet night in July 2025, the stars seemed to whisper a secret that would shake the foundations of astronomy. High above the Earth, the ATLAS survey telescopes locked onto a faint streak of light moving at a blistering 60 kilometers per second, fast enough to outrun the sun's gravitational embrace. This wasn't just another comet or asteroid, it was 3II/ATLAS, the third interstellar visitor ever detected in our solar system. Unlike anything astronomers had seen before, this cosmic intruder, a massive boulder estimated to be between 3 and 7 meters wide, was rewriting the rules of how objects move through space. Its orbit was shifting in ways that defied gravity, solar radiation, and even the powerful gas jets that typically nudge comets off course. As observatories worldwide scrambled to track it, one question burned brighter than the stars. What invisible force was steering this giant through our cosmic backyard? Buckle up, because this is a story of mystery, discovery, and the relentless pursuit of answers that could change how we see the universe. Let's dive into the enigma of 3II/ATLAS and explore why its journey is keeping scientists up at night. Picture the solar system as a vast, orderly stage where planets, asteroids, and comets dance in predictable patterns, choreographed by the unyielding pull of gravity. For centuries, astronomers have mapped these movements with precision, turning chaos into equations. But on July 1st, 2025, that stage was disrupted by an uninvited guest. The ATLAS survey, a network of telescopes designed to hunt for near-Earth objects, spotted something extraordinary, an object hurtling through space at nearly 60 kilometers per second, a speed that screamed outsider. This was no ordinary comet born in our solar system's icy fringes. It was 3II/ATLAS, a massive interstellar wanderer, likely born around another star, now streaking through our cosmic neighborhood on a path that would never bring it back. What made 3II/ATLAS stand out wasn't just its speed. Its size was staggering, potentially up to 7 meters in diameter, rivaling the scale of Halley's Comet, one of the largest comets in our solar system. For context, Halley's Comet, a celestial icon, measures about 7 miles across, and it's considered a giant. But 3II/ATLAS wasn't just big, it was moving in a way that defied explanation. Its orbit was hyperbolic, a near straight shot through the solar system with an eccentricity of over 6, a value so extreme it was practically unheard of. This wasn't a gentle arc or a looping path, it was a high-speed dash, as if 3II/ATLAS had somewhere else to be. As astronomers trained their telescopes on this cosmic heavyweight, they noticed something even more unsettling. The object's trajectory was veering, subtly, almost imperceptibly, but enough to set off alarms in observatories from Mount Palomar to La Palma. Orbital modelers, the unsung heroes who crunch numbers to predict celestial paths, ran their calculations again and again. Gravity, the sun's radiation, even the jets of gas that typically push comets around. None of these could fully account for the shift. The math, the very rule book that had governed every comet and asteroid ever tracked, was failing. For a field built on precision, this was more than a glitch. It was a crisis. If something this massive could break the rules right in front of humanity's best instruments, what else might we be missing? The stakes were no longer just about one object. They were about the limits of our understanding of the cosmos itself. To understand why 3II/ATLAS is such a puzzle, we need to step back and look at how comets move. Imagine a comet as a dirty snowball, a frozen mix of ice, dust, and rock tumbling through the void. When it gets close to the sun, the heat transforms it. Ice trapped within the comet's nucleus begins to vaporize, turning into gas that bursts out in spectacular jets or subtle leaks. These jets act like tiny thrusters, giving the comet a nudge that can alter its path. It's a bit like letting go of a balloon and watching it zip around as air escapes. This process, called outgassing, is chaotic but predictable. Astronomers have spent decades turning this chaos into math, building models that account for every puff of gas and speck of dust. The Rosetta mission to Comet 67P/Churyumov-Gerasimenko gave us a front row seat to this cosmic dance. Rosetta watched as just 10% of 67P's surface produced powerful plumes that not only shifted the the comet's path, but even changed how fast its nucleus spun. These outbursts, fueled by water ice turning to vapor, could push a comet thousands of kilometers off its predicted course over time. The math is straightforward. The more gas a comet releases, and the faster it escapes, the bigger the push. For a typical comet, water vapor does most of the work, blasting out at hundreds of meters per second and carrying dust along for the ride. But the effect depends on the comet's mass. A small, lightweight nucleus is easy to budge, like a feather in the wind. A massive one, like 3II/Atlas, is a different story. It's a boulder that resists even the strongest jets. This is where 3II/Atlas throws a wrench into the works. With a nucleus potentially billions of tons, it's in a weight class far above most comets. To move something this massive, you'd need outgassing on an unprecedented scale. Yet when astronomers looked at the data, the numbers didn't add up. The jets were active. The coma, a glowing cloud of gas and dust surrounding the nucleus, was thick, but the force they generated was nowhere near enough to explain the orbital shift. The rulebook, built on decades of observations and missions like Rosetta, was suddenly incomplete. For the first time, astronomers were staring at a comet that refused to play by the rules. As if the orbital mystery wasn't enough, 3II/Atlas revealed another layer of strangeness. Its chemistry. The coma, that glowing halo around the nucleus, is more than just a pretty sight. It's a chemical fingerprint, a clue to what the comet is made of. When the James Webb Space Telescope turned its gaze on 3II/Atlas, the results were jaw-dropping. For every molecule of water vapor in the coma, there were 8 molecules of carbon dioxide, an 8-to-1 ratio that's off the charts, even compared to the quirkiest comets in our solar system. Most comets are dominated by water, with carbon dioxide playing a minor role. Here, carbon dioxide was running the show, pouring off the nucleus at a staggering 129 kilograms per second, dwarfing the 6.6 kilograms per second of water. This chemical oddity raised eyebrows, but it didn't solve the mystery. In theory, more gas means more push. Each molecule is a tiny kick, like a rocket firing in miniature. But even with this torrent of carbon dioxide, the math still fell short. For an object as massive as 3II/Atlas, the jet simply didn't have the horsepower to explain the observed drift. The momentum was missing. Then, the Very Large Telescope in Chile picked up something even stranger. 22 distinct emission lines from atomic nickel, but no trace of iron. In cosmic materials, nickel and iron usually go hand in hand, forged together in the hearts of supernovae and mixed in meteorites. Yet here, nickel was flying solo, possibly released by exotic organometallic compounds or nanograins breaking down under solar heat. The nickel production rate, about 4.7 times 10 to the 22nd atoms per second, surged as the comet neared the sun, adding another layer of intrigue. Even the dust output, measured by Hubble at 6 to 60 kilograms per second, was significant but not enough to tip the scales. The coma was a chemical spectacle, thick with carbon compounds and glowing with unusual signatures, but it still couldn't account for the orbital deviation. The natural engine was running full tilt, yet the needle wasn't moving far enough. Something was missing, and astronomers were running out of usual suspects. If 3II/Atlas feels like deja vu, it's because we've been here before. In 2017, another interstellar visitor, Oumuamua, sent shockwaves through the astronomical community. Barely 400 meters long, this cigar-shaped shard shot through the solar system at a speed that guaranteed it would never return. But speed wasn't the real shock. As astronomers tracked its path, they noticed a tiny persistent push, an acceleration of about 17 millimeters per second squared that gravity alone couldn't explain. There was no visible coma, no jets, no dust, just a dry, tumbling rock moving as if nudged by an invisible hand. Theories about Oumuamua piled up faster than the headlines. Some suggested outgassing, perhaps hydrogen or something never seen before. Others proposed radiation pressure or even wilder ideas like an artificial origin, but no explanation fully closed the gap. The object was gone before we could study it further, leaving behind more questions than answers. Now, 3II/Atlas was echoing that same mystery, but on a far grander scale. At at thousands of times the mass of Oumuamua, its orbital shift required a force orders of magnitude larger. Yet, just like its predecessor, the standard playbook, gravity, gas jets, solar radiation, was coming up short. The parallels are eerie. Both objects are interstellar, both defy prediction, and both hint at a pattern. Interstellar visitors aren't just rare, they're unpredictable, rewriting the rules with every pass. For astronomers, this isn't just a curiosity, it's a challenge to everything we thought we knew about how objects move through space. If our models can't handle 3II/Atlas, what else is slipping through the cracks? The universe, it seems, is pitching curveballs, and we're still learning how to swing. To grasp the scale of the problem, consider the sheer bulk of 3II/Atlas. This isn't a lightweight pebble drifting through space. It's a cosmic boulder with a mass estimated in the billions of tons. For comparison, the Rosetta mission measured jets on Comet 67P that could shift a mountain-sized chunk by a few kilometers per orbit. But 3II/Atlas is in a different league. Its inertia is like a freight train, soaking up momentum with ease. Every molecule of gas it throws off is a whisper against that unstoppable force. The math is brutal. The usual comet equations say that more mass means less motion from outgassing. A small comet can be nudged thousands of kilometers by a few strong jets, but a giant like 3II/Atlas requires a force that dwarfs anything we've seen. Even if every square inch of its surface was erupting with gas, the total momentum still wouldn't add up. The orbital shift, subtle but persistent, demands something more, something the standard playbook can't provide. Astronomers are left grasping at straws. Could the nucleus be less dense than it appears? A loose rubble pile rather than a solid boulder? The coma's chemistry doesn't support that idea. Could a hidden crack have split open, shifting the center of mass? There's no evidence of a major breakup. Every explanation is stress tested, and every time, something doesn't fit. The problem isn't subtle, it's screaming at us from the data. When the usual suspects fail, science sometimes turns to the unconventional. Harvard astronomer Avi Loeb, known for thinking outside the box, has floated a possibility that sounds like it belongs in a sci-fi novel. In a 2023 paper, Loeb suggested that a thin, ultralight structure, think a cosmic solar sail, could ride sunlight alone, producing a force too subtle for current models to catch. For Oumuamua, a small, lightweight object, the math worked. For 3II/Atlas, with its massive bulk, the idea stretches credulity, but it's not impossible if the object is hollow or designed for maximum surface area. No one in the mainstream is calling 3II/Atlas artificial, not yet, but the fact that such ideas are even on the table speaks volumes. When gas jets, gravity, and radiation can't explain the motion, physics demands another answer, natural or otherwise. Each failed explanation amplifies the question, what exactly are we looking at? The universe is forcing us to confront the limits of our knowledge, and 3II/Atlas is the messenger. The deeper astronomers dig into the mystery of 3II/Atlas, the more they realize they're standing at the edge of the unknown. Every data point, every observation adds another piece to a puzzle that refuses to snap together. The object's high eccentricity, its chemical anomalies, and its inexplicable orbital shift are like clues in a cosmic detective story, each one pointing to a truth just out of reach. Consider the scale of this enigma, an object billions of tons in mass, moving at speeds that defy the sun's grasp, yet nudged by a force that no known mechanism can fully explain. The global network of observatories, from the high-altitude telescopes in Chile to the space-based eyes of Hubble and James Webb, all confirm the same thing. The residuals, the tiny gaps between where 3II/Atlas should be and where it actually is, persist across data sets. These aren't errors or glitches. They're evidence of something new, something that challenges the very foundations of orbital mechanics. The question isn't just about what's pushing 3II/Atlas. It's about whether our understanding of the universe is robust enough to handle objects that don't play by our rules. Could this be a fluke, a 1 in a billion quirk of nature? Or is it a sign that interstellar objects operate under principles we've yet to uncover? The implications ripple outward, touching not just astronomy but our broader quest to understand the cosmos. If we can't predict the path of one massive visitor, how can we trust our models to catch the next one, or the one after that? The universe is vast, and 3II/Atlas is a stark reminder that it's also full of surprises, waiting to upend our assumptions the moment we think we've got it all figured out. The story of 3II/Atlas isn't just about a single object, it's about humanity's relentless drive to make sense of the unknown. For centuries, we've looked to the stars, weaving stories and equations to explain their movements. From Ptolemy's geocentric models to Kepler's laws of planetary motion, each discovery has been a step toward unraveling the universe's secrets. But every so often, something like 3II/Atlas comes along, a cosmic curveball that forces us to rethink everything. This interstellar visitor is more than a scientific anomaly, it's a call to curiosity, a challenge to the brightest minds to push beyond the known and wrestle with the impossible. Imagine the astronomers hunched over their screens, poring over data late into the night, their coffee growing cold as they chase the elusive answer. They're not just crunching numbers, they're grappling with the limits of human knowledge, asking questions that echo across generations. What else is out there? What forces shape the paths of objects born under alien suns? The mystery of 3II/Atlas is a reminder that science isn't a destination, it's a journey, one that thrives on uncertainty and thrives on the courage to question. For every answer we find, a dozen new questions emerge, each one pulling us deeper into the cosmic unknown. This object, with its strange chemistry and defiant orbit, is a testament to the power of wonder, urging us to keep looking up, keep asking why, and keep chasing the truths that lie just beyond our grasp. Beyond the equations and the orbital plots, 3II/Atlas offers something even more profound, a glimpse into the universe's distant corners. Interstellar objects like this one aren't just rocks, they're time capsules, carrying the chemical and physical signatures of the star systems where they formed. The carbon dioxide dominance, the solitary nickel emissions, the sheer mass of this cosmic boulder, they all hint at a birthplace we may never see, a world forged in the crucible of a faraway star. Every molecule in its coma, every atom in its dust, tells a story of a place where the rules might be different, where the physics we take for granted might bend in unexpected ways. As 3II/Atlas streaks through our solar system, it's like a letter from another galaxy, written in a language we're only beginning to understand. The challenge now is to decode that message before it vanishes into the void. With the Vera C. Rubin Observatory poised to detect dozens more interstellar visitors each year, we're on the cusp of a new era in astronomy, one where objects like 3II/Atlas become not anomalies but opportunities. Each one is a chance to learn about the chemistry, the physics, and perhaps even the history of worlds beyond our own. What secrets do they carry? What stories do they tell about the stars that birthed them? The answers are out there, encoded in the paths of these cosmic wanderers, and 3II/Atlas is leading the way, daring us to follow. The journey of 3II/Atlas is a reminder that the universe is a symphony of chaos and order, where the predictable and the inexplicable coexist in a delicate dance. Every comet, every asteroid, every planet follows a path shaped by forces we've spent centuries trying to understand. Gravity, radiation, the subtle push of outgassing. Yet 3II/Atlas is a discordant note, a melody that doesn't fit the score. Its orbit, with an eccentricity of 6.141, sketches a trajectory so sharp and direct it feels almost defiant, as if the object is determined to chart its own course through the cosmos. The residuals in the data, those tiny deviations between prediction and reality, are like whispers of a hidden truth, hinting at a force we can't yet name. Astronomers have long prided themselves on their ability to reduce the universe to equations, to capture its vastness in lines of code and orbital plots. But 3II/Atlas is a humbling reminder that the universe is under no obligation to make sense to us. Its chemical composition, with carbon dioxide outpacing water and nickel standing alone without iron, suggests a formation process unlike anything in our solar system. Perhaps it was born in a star system with a different elemental makeup, or perhaps it endured a journey so long and violent that its surface was reshaped in ways we can't yet imagine. The data from Hubble, James Webb, and the Very Large Telescope paint a picture of an object that is both familiar and alien, a paradox that challenges our assumptions about what's possible in the cosmos. As we track its path, we're not just observing a single object, we're witnessing a clash between our expectations and the universe's reality, a moment where the rules we've written are tested against the infinite creativity of the stars. The discovery of 3II/Atlas isn't just shaking up astronomy, it's sending ripples through science and society, rekindling our collective fascination with the unknown. This interstellar visitor has captured the imagination of scientists, students, and dreamers alike, sparking debates in lecture halls, online forums, and even around dinner tables. It's a reminder that the universe is a place of wonder, where every new discovery can challenge our worldview and inspire us to ask bigger questions. The anomaly of 3II/Atlas has already prompted calls for new research, with teams around the world proposing innovative ways to study interstellar objects. Everything from advanced spectroscopic analysis to hypothetical missions that could intercept these visitors before they slip away. The public's interest is palpable too, as people share theories about what 3II/Atlas might be, from a natural oddity to a relic of an alien world. This isn't just a scientific puzzle, it's a cultural moment, a chance for humanity to reconnect with the awe and curiosity that drove us to explore the stars in the first place. The implications extend beyond academia, touching on how we fund science, prioritize space exploration, and prepare for the unexpected. If interstellar objects like 3II/Atlas can defy our models, what does that mean for our ability to predict and protect against cosmic threats? The asteroid that ended the dinosaurs was a local object born in our own solar system. An interstellar visitor, with its unpredictable path and unknown composition, could pose a different kind of challenge, one we're only beginning to understand. By studying 3II/Atlas, we're not just chasing a mystery, we're investing in our future, ensuring that we're ready for whatever the universe throws our way. At its core, the story of 3II/Atlas is a call to adventure, an invitation to explore the unknown and embrace the mysteries that lie beyond our current understanding. This massive, rule-breaking object is a beacon, drawing our attention to the vastness of the cosmos and the limits of our knowledge. It's a challenge to the next generation of scientists, engineers, and explorers to pick up the torch and push the boundaries of what's possible. Imagine the possibilities. New telescopes designed to track interstellar objects with unprecedented precision, spacecraft capable of rendezvousing with these cosmic wanderers, or even AI-driven models that can predict the unpredictable. The mystery of 3II/Atlas is a spark, igniting a fire of curiosity that could lead to breakthroughs we can't yet imagine. It's a reminder that the universe is not a static place, but a dynamic, ever-changing frontier, full of surprises waiting to be uncovered. For every question 3II/Atlas raises, it offers a chance to grow, to learn, and to redefine our place in the galaxy. As we stand on the cusp of a new era of discovery, with observatories like Vera C. Rubin poised to reveal dozens more interstellar visitors, we're reminded that the cosmos is a story still being written, and we're all part of it. So let's keep our eyes on the stars, our minds open to the impossible, and our hearts ready for the next great adventure. The universe is waiting, and 3II/Atlas is just the beginning. The saga of 3II/Atlas exposes the fragile balance at the heart of our attempts to predict the cosmos. Astronomy is a science built on the assumption that the universe, for all its vastness, operates under rules we can measure and model. From Newton's laws to Einstein's relativity, we've constructed a framework that lets us map the paths of planets, stars, and comets with astonishing accuracy. Yet 3II/Atlas is a stark reminder that our models are only as good as the data they're built on. And when something truly alien enters the scene, those models can falter. The object's orbital deviation, small but persistent, is like a crack in the foundation of celestial mechanics, forcing us to question the tools we rely on. Every observation of 3II/Atlas is a test of our predictive power, a challenge to the algorithms that crunch terabytes of data to forecast where a comet should be. The residuals in the data, those maddening gaps between prediction and reality, aren't just numbers. They're a call to rethink our assumptions about mass, momentum, and the forces that shape the cosmos. Could there be an unknown interaction at play? Perhaps a subtle interplay of magnetic fields, or an undiscovered particle affecting the comet's path? Or is it simply that our instruments, for all their sophistication, are missing a critical piece of the puzzle? The global effort to track 3II/Atlas, involving observatories from Hawaii to the Canary Islands, underscores the collaborative spirit of science, but it also highlights our vulnerability. If we can't fully explain the motion of one interstellar object, how can we be confident in our ability to track the countless others that that may cross our path. This fragile balance between what we know and what we don't is what makes 3II/Atlas so compelling. It's not just a scientific challenge, but a philosophical one, urging us to embrace the uncertainty that comes with exploring the unknown. As 3II/Atlas streaks through our solar system, it leaves behind more than just a trail of gas and dust. It's carving a legacy that will shape the future of astronomy for decades to come. This interstellar visitor is a turning point, a moment when the universe reminded us that it's still full of surprises, waiting to challenge our assumptions and push us toward new horizons. The questions it raises about orbital mechanics, chemical composition, and the very nature of interstellar objects are already inspiring a new generation of scientists to rethink their approach. Research teams are proposing bold ideas, from deploying fleets of nanosatellites to study future visitors up close to developing new computational models that can account for the anomalies 3II/Atlas has revealed. The object's unique chemistry, with its carbon dioxide dominance and solitary nickel emissions, is prompting a reevaluation of how we classify comets, blurring the line between what's normal and what's alien. Beyond the science, 3II/Atlas is a cultural touchstone, a symbol of humanity's enduring quest to understand the cosmos. It's sparking conversations not just in academic journals, but in classrooms, social media, and public forums, where people from all walks of life are wrestling with the same questions. What is this thing? Where did it come from? And what does it mean for our place in the universe? As we prepare for the flood of interstellar objects that the Vera C. Rubin Observatory will soon reveal, 3II/Atlas stands as a pioneer, a harbinger of the challenges and opportunities to come. Its legacy will be measured not just in the data it leaves behind, but in the curiosity it ignites, the collaborations it fosters, and the discoveries it sets in motion. In a universe that's constantly changing, 3II/Atlas is a reminder that our understanding must evolve too, adapting to the unexpected and embracing the mysteries that make the cosmos so endlessly fascinating. The story of 3II/Atlas is just the beginning. As we speak, the Vera C. Rubin Observatory is gearing up for its 10-year legacy survey of space and time, set to revolutionize how we hunt for interstellar visitors. When it comes online, astronomers expect to spot dozens of these objects every year, each one a time capsule from another star system, carrying clues about its origins. 3II/Atlas isn't a one-off. It's the first wave of a flood. Each new detection is a chance to catch another rule breaker, another outlier that challenges our understanding. But here's the catch. If our models can't handle 3II/Atlas, how will they fare against the dozens, maybe hundreds of interstellar objects to come? The universe isn't just throwing curveballs, it's pitching blindfolded. Every anomaly is a reminder that our grip on the cosmos is only as strong as our willingness to question it. These objects aren't just rocks, they're messengers from other suns, carrying the chemistry and history of worlds we'll never visit. If we want to understand our place in the galaxy, we have to chase every mystery, every unexplained orbit, every hint of the unknown. So, why should you care about a giant rock hurtling through space? Because 3II/Atlas isn't just a comet, it's a challenge to everything we think we know. It's a reminder that the universe is vast, unpredictable, and full of surprises. Every unexplained orbit is a chance to rewrite the rulebook, to push the boundaries of science, and to glimpse the bigger picture of our place in the cosmos. This is a story that's still unfolding, and the next chapter could change everything. What do you think 3II/Atlas is? A natural oddity, a cosmic fluke, or something stranger? Drop your thoughts in the comments below and let's spark a conversation. If you're as fascinated by the mysteries of the universe as we are, hit that like button to show your support and share this story with someone who loves a good cosmic puzzle. The universe is calling, and 3II/Atlas is just the beginning. Stay curious and let's keep chasing the unknown together.